Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To the Big Data Platform session. I'm Surajit Chaudhary. I'm the session chair. In other words, I don't do anything. The main important thing I want you to all remember that if you want to ask a question, we do want to record it. So there are folks with microphones, so just raise your hand and we'll get the microphone to you. That's sort of the most important thing I wanted to say. I'm going to get out of your way. There are three excellent speakers today. We're going to have the first talk given by Raghu Ramakrishnan. I'll introduce him in a minute. He's going to talk broadly about thinking on big data at Microsoft, looking from our business group's perspective. The second speaker is Stoica from University of California, Berkeley. And the final speaker is, and he's going to talk about really a pretty complete stack on data analysis, data analytics platform. And finally, we'll have Vivek Narasayya from XCG of Microsoft Research speaking on the multi-tenancy in the context of cloud data platforms. So with that, let's get started. So Raghu Ramakrishnan, as you all know, doesn't really need an introduction, but let me say a few words. He is the technical fellow here at Microsoft in our Cloud and Enterprise division, which is the new name. Earlier name used to be Server and Tools. Before that, he was at Yahoo, where he was a chief scientist as well as a Yahoo fellow. And during that time, he worked on a number of very significant projects, including Peanuts, which many of you would know as a geo-replicated data platform. Prior to that, he was at University of Wisconsin-Madison, many years in faculty. He wrote a book that many of you may have read or taught from, as a Sigma 10-year award, as well as Sigma Contributions Award. With that, Raghu, the stage is yours.
Okay. Let me make sure. Is this the one to go in here? Thanks. Before this, you need to tell me which of these actually goes in here. And you're not taking these minutes off of me.
You're connected, right?
I'm connected, but my slides are not.
Connected to, is it noted what it is?
Just try next. I can connect it to whichever you like. That's easy.
We have like 8 PC connections possible, so we're basically doing a sequential search.
All righty. Success. So, glad to be here talking to you guys. I do want to give you a bit of a frame for what you're about to hear, because my position is in the product team, but running an applied research group. So to that extent, I will give you the perspective from the applied research group. There's not really a product roadmap, but it is informed by thinking around the product roadmap. Okay? The outline of this talk, I'll talk roughly about our notion of where the field is headed in terms of big data and usage of big data in particular. And time permitting, I'll drill down into a couple of things in a little more detail: tiered storage and the notion of a universal compute fabric, scale-out compute fabric. Sizzle is the name of the group. I thought I'd at least put in a plug for the team here. But let's get to big data because time is short. I'm not going to try and define big data. It's a buzzword and I don't like it. But since it's a buzzword that's with us, I thought I'd define what's interesting about it through examples, right? What's really interesting in my mind is not so much the technology as all the different uses of big data that are driving where we are headed, okay? And it's a convergence of factors that has made this really important, really rapidly, explosively rapidly growing. First, cloud delivery as a form factor, okay? You can rent instantaneously. Second, analytics, everything from visualization to interactive querying to predictive techniques. We've had advances that are pretty exciting, especially if you can bring these to bear at scale, right? Lastly, costs have plummeted. The cost of capturing data and storing it has gotten to the point where the default is to do so, okay? There's enormous value in the data. The cost has gone down. Why not keep it and try to get the value out of it? That's the current trend. And all this is happening really, really fast. I'll give you a couple of examples drawn from my earlier work at Yahoo, but there are parallels to this over in MSN and Bing as well. First, look at the problem of content optimization. When I went to Yahoo, the whole page, the front page, was static, meaning editors manually determined every link you saw on the page. Today, virtually the entire page is dynamic. Every link you see is put there by an algorithm, okay? And it's not just the front page. Over, I don't know, north of 95% of all Yahoo traffic today goes through pages that are optimized in this fashion. If you think about what this involves, right? So if you take the set of 4 articles you see there, they are selected from some underlying pool of articles that editors prepare. In order to decide what goes into the pool, editors have access to a lot of dynamic dashboards, okay? I'll give you an example of that in a moment. Based on this, the algorithm is able to choose some 4 out of the pool, which 4 it chooses, and in which slots it places those selected 4 has a huge impact on click-through. In the 3 or 4 years that this has been operational at Yahoo, the click-through rate relative to the best manual editors went up by over 300%. Okay? What does it take to do this? First, you need to be able to analyze content like articles and captions and multimedia. You need to be able to look at activity traces. If I show someone an article in Shanghai, then in a matter of minutes, 5 to 10, what I showed them, what they clicked or ignored, this data is available. It's folded into the machine learning algorithms that decide what to show the next person who views the page, and perhaps they're in Sunnyvale. Okay? It's data coming from thousands of servers worldwide, streaming in. You're looking at a wide range of data, all the way from loosely structured log records to along the way as you go down and create the charts like this, highly structured data as well. Okay? And you might ask, okay, so the web companies do this, why should I care? Well, if you think about things like Office 365, something foundational is happening. Enterprise applications, as they move to the cloud, everything in there becomes observable. In the same way that I can look at what you did when I showed you a web page, I can start to analyze what you did at every stage in your use of an Office product. And therefore, the same opportunity to optimize these enterprise products is now in front of us. Okay? And it'll have the same kind of informational opportunities and challenges. Telemetry. As we deploy thousands of servers ourselves on the cloud, everything from capacity planning to forecasting possible outages to identifying who might be the team that's responsible for a particular, for looking at a particular outage cause. These are things that we need to get to be very, very good at. Again, if you look at the common characteristics of the underlying data, wide range of data, enormous volumes, you need to make near real-time decisions. How do we do this? So I could go on and on with many more examples, but hopefully you get the idea. This brings us to the question of, in order to support applications like this, and don't forget traditional applications, they aren't going anywhere, right? But we also need to support these. What should we build? In a nutshell, this is the answer we've been noodling. Let me call this the digital shoebox. One place, logically, where you can keep all your data, whether it is relational tables, graphs, machine learned models, whether it's documents, multimedia. You shouldn't have to put each of your different types of data in a different place so you can do the right kind of analysis. All of your data in one place, you're able to do best of breed analysis for each of these different types of data, different types of scenarios, and you're able to create end-to-end composite analysis by mixing and matching the right things. So you might use SQL to do filtering and feature creation, and then you might use a machine learning algorithm to fit a model to observed cases. Okay? You should be able to do all of this in one place. How do we get there? So, first, I think there is a notion of tiered storage that we need to wrap our heads around. Okay? And I'll say a bit more about this. Given the goal of storing all of your data, ranging from high-value data for which you're willing to pay a premium, to things like machine traces, where if you lose some chunks of them, it's okay, as long as you don't lose them too often and too much. The price people are willing to pay for storing this data is going to vary. You're going to store it in many different ways, but yet you need to play the game of having it available to you when you need to compute. A scale-out compute fabric. If you look at a SQL engine, a machine learning suite, a graph analytic tool, BI, you can't build these stacks from scratch in a scale-out manner over and over. We just can't afford to do that, right? If you look at the number of nodes in a typical computation on, say, Hadoop or Cosmos, these are in the hundreds or the thousands. There's a lot of work that goes into making these kinds of scale-out computations possible that is agnostic to whether you're talking about SQL or machine learning. And this common part, you need to find a way to factor it out and reuse it. That's what I mean by the scale-out compute fabric. Once you have that, you can build different stacks, maybe a relational stack, maybe a machine learning stack, and so on and so forth. This is the big picture that we are working towards. There are many questions that come up here. When you go from PowerPoint slides to real code, what are the right trade-offs? What should be in the common tier? What is unique to each engine, right? How do you layer things to get this right? What happens when you have multi-tenanted services in all of this? On and on. Complicating this are some very challenging issues. The volume you're dealing with is enormous. Even if any one enterprise customer is not at the scale of a Yahoo or a Google, collectively, that's what the scales look like, right? On any given computation, one of the opportunities you have now is to elastically burst up, to take free compute resources if they happen to be available. Equally, you need to have flexible ways to give back allocated resources that you don't have necessarily a right to if someone with a higher priority comes along. How do you do these kinds of things cleanly? Metadata becomes much more complicated here. Real-time, OLTP, interactive, the demands for all of these are growing. And when you combine them with scale-out, you have a tough problem on your hand. When you do multi-tenanted services, okay, high availability, rolling upgrades, these kinds of challenges can make all the difference between a successful service and a nightmare. How do we do this? So far, I've talked mostly about analytic workloads. What exactly should be our position relative to transactional or CRUD workloads? Do you expect them to run off the same stack, or do you have distinct stacks with loose coupling? Okay? These are all hard architectural questions for which we don't have easy answers. Let me make a few more remarks about tiered storage in particular. The big insight behind Hadoop and scaling computation out was the following. Spray your data out over thousands of commodity servers and spray your computation out by farming it out to where the data is. And where the data is essentially meant situate your compute on the machines whose disks contain the data you want. Today, there are some changes happening. First, let me talk about Azure. Azure has a tier called Windows Azure Storage that's optimized for low-cost bytes. However, part of the optimization means that you're not allowed to actually do computation on this tier. Okay? Not only that, there are other even cheaper tiers of storage, like tape storage, which you also have to deal with. Your data might be there. In the other direction, main memories are exploding in size. Things like NVRAM, SSDs, flash, as these become available, the spectrum between the closest data and the farthest data, that distance ratio, is growing. This means database people have job security for life, right? But it also means something else for people building these scale-out systems. You now have to play two games simultaneously. You have to think about how to cache data across tiers, okay? And cache data not with respect to any one analytic framework or workload like SQL, but in a way that recognizes that your workloads are now heterogeneous, okay? And right alongside this caching game, you now have to figure out how to schedule compute near cached data. How do you do this, okay? This brings up some pretty challenging issues, as you might imagine. Now let me get to the compute fabric. So the first generation of MapReduce was really, the code was monolithic. If you wanted to do SQL, you did it by translation into MapReduce. The second and third generation will not look like this. They're simply not efficient enough, okay? But then, how do you get to a refactored architecture where some of the common pieces are reusable? The first step in this refactoring is arguably the wave of resource managers. From Yarn to Mises to Corona, right? People have recognized that the basic problem of keeping track of how the collective computing resources in a large cluster are being used, and then handing out resources on demand across competing job requests. This is a foundational building block that you can factor out and reuse. Whether your job is MapReduce, whether it's SQL, whether it's ML, there are some commonalities here. But then, that's a first step. We actually believe there's a whole lot more that needs to be refactored. When you look at the actual implementation of something like MapReduce, there's a whole lot more than just the resource allocation. This is, if you take Yarn, this is the version of the resource manager that we are working with. It's associated with Hadoop 2.x. Hortonworks has been driving this. We have been working closely with them. There are many others there though. A piece of software that we have been working on is called Reef. The idea of Reef is to complement Yarn. If you use Yarn to get containers for a distributed computation, right? Now, each of those containers can be made more usable through the use of Reef as a series of libraries, okay? Everything from storage support, networking, checkpointing, these are available for every task that you have running in one of these containers, okay? So for example, you could have a piece of code running on this machine, and you could protect yourself against failure by using a Reef checkpointing utility. And if this machine subsequently goes down, Reef will help you automatically detect and restart that task on some other machine, and your saved state is automatically made available to it. Okay? That's one example of the kind of additional support you could get. As yet another example, let's say you have been allocated 10 containers and that's all you're going to get. You are executing, you're the implementer of MapReduce here, not the guy submitting a MapReduce program. You can implement MapReduce so that if one of your reduced jobs is gated because it's waiting for some maps to complete, you can suspend this particular reduce, let others go ahead and then bring this back up later without a loss of the work done so far. If you want to do things like this, you need to go beyond yarn. And these are the kinds of things that Reef is designed to help you with as a developer of systems like MapReduce systems, SQL systems, ML systems, and so on. Large cast of characters here. What have we built? We're actually building a version of MapReduce, soup to nuts, to show what this can do, as well as iterative algorithms, machine learning algorithms that scale out. Okay? We plan to open source this. I won't give you a time frame, but think several weeks, few months. Okay? And I hope you will join with us in using and extending this. We are also making contributions to the actual scheduling in Yarn. Okay? Very briefly, what we are doing is work-preserving preemption, mechanisms for it, and scheduling policies that take advantage of these mechanisms. All of this is already in Apache open source. Okay? So this builds on previous work. I'll skip that. Here's the basic idea. Take the example I talked about a moment ago. You have a collection of map jobs, and some reduced jobs have started up there. But there's a straggler map that's blocking a number of the reducers. Instead of having those reducers continue to hog those machines, what if you could preempt them where the red stuff begins and let other work be scheduled that is not blocked by this straggler, right? That would lead to a picture like this, all right? And the gains of doing this can be considerable, right? As opposed to killing the jobs, if you were to preempt them in a work-preserving fashion, you can get completion times up to a third faster. So net-net, we're doing all of this, a whole pile of Jiras in Apache. It's there. It should be there in the next version of Hadoop that you check out. So bottom line, we are actually working with the open source community in a pretty deeply embedded way, which for Microsoft is a pretty big step. Okay? Let me stop here and simply say that whatever I have described, in addition to the people that I mentioned, there's a number of collaborations inside Microsoft with Surajit's team, with MSR in general, various others you see here. Let me stop. Any questions? I'm happy to take them now.
Any questions?
Jignesh.
Yes.
Oh, one
what do you think is the...
Hold on.
So Hadoop v2 is not catching on a lot with the big population of the MapReduce Hadoop community that is out over there. And do you have some thoughts on what's going on? Is it because there are lots of tools already baked into the current version? There's a lot of the effort that's needed to move on to the next version?
So it's unclear to me that it is not catching on. I mean, first off, it's been slow coming out of the chute. Okay? There's been a lot of testing at Yahoo, which was slow, which went slower than expected. But from what I can tell, now that it's becoming available, I think there will be uptake. This would be a good question to discuss, say, 6 months from now, if with availability there isn't uptake, right? So we've been talking to people from Twitter, LinkedIn, places like this, Facebook. I'm going to wait and see. But if you talk Hadoop 2.0, specifically Yarn, I would expect to see uptake. And for a lot of what I'm talking about, Yarn is one of various resource managers. I think the really important bet we are placing is resource management, not necessarily Yarn. Okay? Other questions? Mike? Oh, there's one more question over there. Stan?
Alex. Hello, Alex Wolf. I'm getting the feeling that you're sort of talking from the perspective of an operator of a data center. And I can imagine that there's a whole other, let's say, perspective, which is latency-sensitive jobs, right? How are you addressing or thinking about addressing those kinds of...
Great question. So one of the little boxes that I glossed over said streaming and interactive queries. Okay? That's where this would come in. And your point is valid, though. We are approaching this, the work that I described anyway, is aimed at people within Microsoft or elsewhere who would build systems, right, for various workloads, including the streaming and interactive workloads. So if I take SQL, right, the work I described doesn't directly build a SQL system. It supports someone who builds a SQL system. It doesn't directly build a streaming anything. But if you take people who are working on products like Stream Insight or RX, they could use the framework we're talking about to build a streaming or interactive system on top. So we are one level below that. But we do certainly want to deal with streaming and interactive applications. So we can talk offline if you have more questions. Yep. Question over there, and then Mike. Yes?
So in this world where we have now the ability of collecting and storing tremendous amount of data, where do you think privacy and security should head in order to, be it protect users, protect enterprises, or even protect the data center operators?
There's no easy answer to this, okay? I mean, it's something like, I think when all is said and done, all of this is going to go forward because there's too much to be gained. But there's also tremendous risk in terms of privacy and security, okay? Security is, in some ways, the easier of the stories. Personally, I believe 5 years from now, we'll be seeing consensus that clouds are a more secure way of doing things than having your own private foo. Okay? If nothing, the cloud operator has the chops and enough at stake to really double down on this. Privacy is a much more delicate issue. And let me give you a little anecdote here. At Yahoo, where they were very religious about privacy, so for years, they wouldn't even show you ads based on the keywords in your email, okay? They actually had, I don't know if they still do, a $25 a year subscription, which automatically ensured that no one ever tracked you, you never saw ads, okay? And in fact, you got extra helpings of freebies, okay? The amount of storage, so on and so forth. The number of people who actually used this was vanishingly small, okay? So what that tells me is, commercially, people don't seem to understand what they are giving up in terms of privacy, or they don't care. What I think we as systems builders and this new breed of software as a service provider need to do is to be transparent about the trade-offs and make this as clear as possible and give people choices, okay? Beyond that, I don't really have an easy answer for you.
Okay, Mike, I guess last question or?
Yes.
I'm just curious if you have anything to say about how existing systems and tool sets fit in with the digital shoebox and sort of this bigger vision.
It's a great question. So, and this is particularly relevant to us here at Microsoft, right? Because one of the opportunities I saw when I came here, frankly, was Microsoft has meaningful market share in a range of these little boxes that I drew up there, ranging from analytics to storage, right? And the question that you ask, how are we going to evolve from the current world of several silos to this big, wonderful place in the sky? I think part of the answer is in the right layering, okay? I think if you bring the right abstractions to bear in building tiered storage and the compute fabric, in looking at the analytic pieces, right? An open question, I don't have a universal answer, but case by case, would be how to graft what we have in Go in an evolutionary way, right, onto this new execution fabric. For example, concretely, if I take SQL, if I have a distributed SQL implementation, right, how much of the smarts that we have and have built over 30 years in terms of global planning, query optimization, should carry over. Hopefully a lot, if not all. Not all perhaps, because the scales are different, but okay. Also, we need to bring into play the notion of fault tolerance. How do you cost the impact of a potential fault, right? The cost of caretaking against it and the consequence of just redoing. But still a lot should carry over. On the other hand, the runtime, I think, will look nothing like what our old runtimes look like. Okay? Being able to elastically demand and get resources and operate in this world of faulty but fault-tolerant computing, it's different. And we need to wrap our heads around this. But I hope that we will be able to build on some of the assets we have and not start cold.
Well, thank you, Raghu.
All right.
You can give your thing to Vivek. Not here. So the next speaker is Mike Franklin, and he will be talking on the next steps. Yes, the next steps in DHT. Okay, I mean, you are talking, so I decided I would interrupt you. So I'm very happy to have Professor Jörn Stoica from UC Berkeley to be here to give this talk on Berkeley Data Analytics Stack. Everyone knows him. Just to say a few words, he works broadly in the area of cloud computing, resource management, scheduling, and of course, architecture of the network infrastructure. He has many awards, including he's an SCM fellow and SIGCOMM Test of Time winner, ACM doctoral thesis winner, and many more. So I'm very happy to have him, speak on this. By the way, he's also a founder of a startup. So talk to him about getting shares in his Conviva, which is a video distribution startup. Thank you.
Thank you. So I'm going to talk about this Berkeley Data Analytics Stack, or for short, BDAS. We are building at Berkeley, and this is the main deliverable of the AmLab, which is this multidisciplinary lab at Berkeley, which is led by Mike Franklin here, and which among founders also includes and sponsors includes Microsoft. So like Raghu, instead of defining the big data, let me say a little bit about how people use this big data. What do they use for? So they use for many things. But if you want to categorize, they use it for reporting, to track business processes, transactions. They use it for diagnosis. Why the user engagement is dropping. They want to find out why the system is slow, or detect spam, denial of service attacks, and so forth. But most importantly, people use big data or intend to use a big data for making decisions. Because this is a way, ultimately, to extract value out of the big data. Examples are personalized medical treatment, decide what features to add to a new product. This is what you do with A/B testing. Or the canonical examples of our times, it's decide what ads to show, or what information to show to a particular user. So really, a lot of our research within the AmLab is driven by this belief that data is only as useful as the decisions it enables. So what does this mean? Well, it means that we want low latency or interactive queries on historical data because, in general, faster decisions are better decisions. We want to have low latency queries not only on historical data, but on live data as well, because the decision we make on fresh data, in many cases, are much better than on historical data. And finally, we want to support not only SQL, but we want to support sophisticated data processing between some decisions and some analyses, like anomaly detections or trend analysis, require sophisticated computation like machine learning, graph-based algorithms, and so forth. So this is what we need. Of course, we are not the first to recognize the need for this kind of applications, and many others did that, and even before us. So what was the reaction? So the reaction was building specialized models to address these target applications. We have Google Pregel for graph processing, more recently Impala for interactive queries, Storm for streaming, iterative MapReduce for iterative computations. Now, the problem with this approach is that it doesn't really cover all the cases. And another one, which is more subtle, it is hard to compose these computations in a single application. So why would you need it? So say you want to detect a denial of service attack. What do you need for that? One, you want to do it in real time. So you need to operate on streaming data. Next, you want to figure out, the surge in traffic, is that a denial of service attack or is just something natural? So you may want to look at what happened the same hour yesterday or the last week. Or you may want to look at the sources from which you get this load to see, is that normal? Was this the behavior 1 hour ago or again yesterday at the same time? So now you need to be able to query very fast on this historical data. And in order to do that, you need also to probably to pre-process the data. So you keep these nice data structure indexes so that it's easy and fast to query. So you need streaming, interactive querying, and batch computations. So our goal is basically to build a stack which supports batch, streaming, and interactive computations, and make it easy to compose these computations. And another goal, which I am not going to talk too much today, is to make it easy for developers to develop these sophisticated algorithms like machine learning and graph-based algorithms. So what is our approach to provide interactivity, streaming, and of course batch is easier because it's already done, very successful by Hadoop. So there are two main observations. So one, we want to leverage memory aggressively. So why is that? This is a high-end data center now today. So it may have between 16 and 24 cores. It may have between 128 and half a terabyte of RAM. It may have between 10 and 30 terabytes of disk drives, and maybe a few flash drives, say between 1 and 4 terabytes. Now all of this entire node is connected probably by 10 gigabits per second Ethernet to the other nodes in the data center. Now let's look about the speed of various buses in the system. So in order, the throughput to the disk and from the disk, as everyone knows, is pretty low, right? For if you have this 10 disk here, you have between 200 megabytes and 1 gigabytes per second. So between 20 megabytes and 100 megabytes per second per disk, sequential access. For flashes, you put that on a PCI Express and so forth, you may get, for 4 disks, 4 gigabytes per second. And for memories, you have 4 DDR3 channels up to 60 gigabytes per second. This is what you have. So the memory bus is still much more faster than disk and even SSDs. The second reason for using the memory is that it turns out that many data sets fit into memory. So actually, we did this study 1.5 years ago. Maybe things changed since then, but I wouldn't expect so. And this was for workloads from clusters from Facebook, Yahoo, and Microsoft Bing. And the inputs of over 90% of the jobs in these clusters, their input fits in memory. And yes, there will be these huge jobs, periodically, every day computing the indexes and so forth, and they are going to use most of the resources of the cluster. But most of the other jobs are pretty small. The other one, just thinking about, right, is that you have 1 terabyte, you have a couple of servers today, or even one server, it has 1 terabyte today. This is 1 billion records, 1 kilobyte each. So it's a lot of data. And the memory density grows with Moore's law. Actually, for the next years, probably it will grow a little bit faster because you have these RAM SSD hybrid memories at horizon. You combine them. So again, this is one thing we do to provide interactivity and, as you'll see, streaming. The other one is how you can speed up things. You can increase the parallelism if you can, right? So here is an example. Say you have a mapper here. You read with 2 inputs from 2 disks, and then you compute an aggregate result. One way to speed it up is that instead of using 2 disks, you can partition the data among 4 disks, and you can read from this in parallel, right? And if this I/O is a bottleneck, like it happens to be in most of the cases, then you are going to have a speed up almost by a factor of 2. Of course, when you do that, you are faced with quite a few challenges. If you really want low latency, you need to have a low latency scheduler. If you look at Hadoop, it takes between 1 and 3 seconds when a slot is available just to schedule a new slot, a new task on that slot. And again, that's because Hadoop was built for a different kind of applications, batch application. Then the highest parallels you have, the most, you need to be worried about the failures, about stragglers. The shorter the task is, it's harder to detect whether there is a straggler. It takes time. So you need to do something there. And then, the communication will eventually become a bottleneck. So you need to optimize for communication as well. So Spark, it's our cluster computing framework. It's the first one we built at Berkeley. And it was targeted to provide support for interactive and iterative computations, such as machine learning algorithms. And basically, it's using these 2 ideas I mentioned about before in providing 2 things, basically. One, it allows you to achieve sub-second parallel job execution. The second one is that enables stages in the same job or jobs to share data efficiently. How you do that? You do this through a resilient distributed data sets, which is in memory, fault-tolerant storage abstraction. It has a low latency scheduler, improved, more efficient communication patterns, and so forth. So next, I'm just going to touch on this RDD, which is the main abstraction behind Spark. So really, the hard problem here, you put the data in memory, that's easy, right? The main problem is that how do you deal with the failures, right? And one simple way is to replicate. This is what Hadoop is doing, actually, HDFS is doing, right? At the storage level, at the disk level. So you can take the data and you replicate on the various machines. Of course, that's not such a great idea, at least for 2 reasons. One, you need to go over the network. So that slows down the write speed. So you have the network speed. And the other one, the memory is still expensive. It's premium. You want to use as much as efficiently as possible. So now if you replicate the data, you are going to hit that you are going to be quite inefficient. So the result here, the answer here, and it's should be quite obvious for many of you, is that first we are going to restrict the RDDs. So the RDDs, what are RDDs? I didn't define them. They are a restricted form of shared memory. They are immutable. It's a partition set of immutable items. And one RDD can be only built through coarse-grained deterministic operations, such as map, filter, and join. And now the solution, this is what I was mentioning that is very familiar to you, the database people, is lineage, right? With each the handle of each RDD, you maintain the sequence of operation which created that RDD. So therefore, when there is a failure, Spark has enough information in that to replace these operations to recreate the RDD. So here is a simple example. So the data, say initially it's on the disk. You read it with a map function, and then you create this RDD with 3 partitions. This is in memory on 3 machines. Then you apply a group by, and you create another RDD. Now this has 2 partitions, after which you apply a filter. And you create another RDD. This will be the result RDD of this kind of job. Now, if this machine fails and this partition disappears, then when someone wants to access that partition, Spark has enough information to know that this partition has been built from this previous partition by a filter H, and is going to replace that operation and rebuild the partition. If you build, of course, this generalizes. If you build this kind of last two partitions, you are just going to replay deeper from the hierarchy. Now, the RDDs have two key limitations. One, they can only be created by coarse-grained operations, and the second one, they are immutable. However, it turns out that they can express a surprisingly number of parallel algorithms. And these are algorithms which naturally apply the same operation to many items, so you can batch this transformation of many items. So it can unify current programming models such as data flow models, MapReduce, Dryad, SQL, and even specialized model for iterative applications like Pregel, iterative MapReduce, and GraphLab. Okay, and if you think so, it kind of is expected. Like if you think about HDFS or GFS, right? It's append-only file system, right? Still, it's useful for a large number of applications, certainly much larger than what people envisioned when they built these file systems. And in addition to that, Spark with RDD supports new applications that this model don't support. What I mean here, it allows applications which can compose these models, right? It's one system. So a few performance numbers. So here is PageRank compared with Hadoop. Of course, you are doing much better. The data, after all, is in memory. It's between 6 and 8 times. This is for 30 nodes and 60 nodes. And depending on the algorithm, you can do even better. This is K-mean and logistic regression. For K-mean, we do like 40 times better almost. And for logistic regression, 2 order of magnitude better. The difference between our improvements are due to actually communication. So you have different, the communication. It's when you do not that well, the communication becomes a bottleneck. Now, I am a networking person, and when Raghu is talking about layering, one question is that in networking, or at least I used to be, is that what is the narrowest? Right? That's the question. So our answer, at least at this point, is Spark. Spark is our narrowest. It's the execution engine on which everything else is built, and Spark is also accommodates a variety of storage infrastructures. Now, I'm lying a little bit about it because in order to have this nice narrow waist, I left out some of the other components we built, like Mesos, which is kind of a little bit hard to depict here. But anyway, so in terms of if you are talking about data processing, Spark is our narrowest. And like I mentioned so far, Spark provides support for interactive and iterative computation, and of course batch, right? Trivially. What about streaming? So to provide our support to streaming, for streaming to Spark, we build this other component, Spark Streaming, which is part of Spark, as the name implies. And let me briefly present it. So existing streaming systems are like what, you have this DAG of operators, and they are long-running operators, stateful operators, and the records come in, and each of these operators ingests the records, modifies the state, and maybe create another record which will be sent to the next operator on the operator graph. Okay, so and this works pretty well. I think that what are the challenges? The challenges is that it's pretty hard to ensure fault tolerance. It's not impossible. There are there's a lot of work in this area, but it's pretty hard. And the fundamental reason it's pretty hard is that there is a lot of state in these operators. So if you fail, somehow you need to recreate the state. So you either do that, you have replicate the computation, or in general, you store the input in some in the input records, and then you checkpoint maybe the state of these operators, and then you have a failure. You start from the previous checkpoint and you replay all the input records. Right? That's what you do. Okay? So what do we do? Right? We do differently. So our main observation inside here is that actually, if you think about Hadoop deals very well with failures and at some level with stragglers, at least. That was the goal. That's what it was built for, right? So the intuition here is that now, if you have, but the problem with Hadoop is that each job takes a lot of time. Now, if you can run a job in less than 1 second, what you can do? Well, what you can do is that you can run a streaming computation as a series of very small deterministic batch jobs. This is what you do, right? You run a job, then save the state, then you run the next job, right? Over and over again, and then you update your results. Okay, so now this is exactly what Spark Teaming is doing. When the live data is ingested, it's chopped out in batches, say X second each, and then these batches are saved like RDDs, and then they are sent to the Spark engine, which performs the computations and returns results in batches. Right? And by the way, when the data comes in, it's not stored on the disk, it's actually stored and replicated in memory. So the first time, there we do replicate in memory. So how fast can it go? It can go pretty fast. So this is an example in which you have, yes, some simple streaming application, a grep and top K word count. And it's up to 100 nodes. So one thing you can see, it scales quite linearly. And it can process over 60 million records per second or 6 gigabytes per second on 100 nodes. This is much faster than Storm, and it's pretty competitive with the commercial offerings. Now, I was saying that we did this, this kind of running a streaming application, a sequence of bad jobs, in order for one of the reasons was for handling the fault tolerance. So how well you do there? Well, so here it's a computation. It's a sliding word count. It's over 30 seconds, running on 10 nodes, and it's 2-second chunks. And you see that in general it takes 1.5 seconds, so it's pretty good. It's end-to-end latency. So each of these bar is the end-to-end latency of how long it takes to process a chunk. And now here at this time, 30, you have a failure. Okay? We use 30 seconds checkpoint. So you need to go back, in this case, probably almost 30 seconds to the checkpoint. So what you see here is that when you have the failure, you just have a little bit of increase, less than 1 second increase in the delay, after which you flatten out and you go back to 1.5 seconds. So why is that? Why is it so much faster? Because you'd expect, again, you'd expect is that, okay, it fails, then I need to rerun all this data I missed to restore the state, right? It will take much more. So why is that? Well, the reason is that actually the recovery happens in parallel. On that node which failed, you have many small RDDs. And when they are recomputed, they can recompute not only one node, but they are recomputed in parallel on many nodes. So that's why it's fast. So you have this parallel recovery. Okay, so I have another 3 or 4 minutes, so what are the other components? Shark is Hive over Spark. Hopefully many of you saw this talk at SIGMOD. So this is 100 times faster when data is in memory, and even when data is on the disk, it's between 5 and 10 times faster due to various optimizations. So what is next? So let me spend just a few minutes on what is next. So one thing we are really looking now is that to trade between result accuracy and response time. So why do we need that? So you remember this figure. We are saying, you have a processor here, you have the memory here. Say you have 0.5 terabyte of RAM, and you have the 60 gigabytes per second bus between the processor and RAM. Now, if you do the math, it turns out that even if data is in memory, just to scan this data, it takes 10 seconds. Actually, it takes more because you have contentions. So therefore, the fact that you have the data in RAM doesn't guarantee you that you are going to be interactive. And the worst thing is that this gap, it's increasing. The memory doubles every 18 months, while this bus, the speed it doubles every 36 months. Right? So the gap is exponentially increasing doubles every 36 months. So this is what we do. It's about BlinkDB, and I'm going to be very quick here. So fundamentally, it's the observation. You don't always need exact answers. And actually, in today's world, it's an open world. You have all this information from which comes, you ingest, is quite noisy. So even if the computation is exact, you are not going to get guaranteed results. And this is what happens with everything you interact in today's world. There are very hard challenges here. How do you compute and estimate errors on arbitrary computation? How do you know, even if you can estimate, how do you know that the estimation algorithm is working? Because there are certain assumptions, and these certain assumptions are hard to check in practice. And more of that, some assumptions are sufficient and not necessary. So there is a gap there. And in addition to that, we are doing raise the level of abstraction now to provide better support for graph-based algorithms and machine learning algorithms. So one of the most ambitious projects now is ML-based, which is a declarative approach to machine learning, and Mike will be happy to answer any questions here. So in summary, this Spark, it's our narrow waist, at least in our Berkeley data analytics stack. It unifies a batch streaming and interactive computations. And as future work, we are looking to raise the level of abstraction to provide better support for sophisticated computation, and these are GraphX and ML-based projects. And we are looking also for speeding up the computation, reducing the cost, is to trade between the accuracy, speed, and cost, and this is a BlinkDB. And there is a vibrant open source community behind some of the components of this stack. It's used by tens of companies, and actually we are very happy that we have actually contributors, not only users, but contributors. Thanks.
Well, thank you, Jan. Questions? Go ahead.
So this is fantastic work, and we're pretty familiar with it. So one thing I'm recognizing, maybe sort of as a question about how we move the research agenda forward, to a first approximation, everybody's 100 times faster than Hadoop, is what I've kind of discovered by watching a lot of talks, right? So how do we get to the point where we stop comparing with Hadoop, but we compare with each other on specific applications and really
how do you compare with?
Move the frontier forward past just beating up on Hadoop.
So how do you compare with the existing work or other? Is that the question?
Yeah, there's literally no talk I've seen in this space over the past 2 years that doesn't have a chart exactly like yours where they're 100 times faster than Hadoop.
So I think that it's a good question, and we start from with very low barrier, right? It's Hadoop for all these things. It's a very low barrier. But I think that as we go and this field matures, you are going to see more meaningful and better comparisons. Actually, we do have, for instance, we run a benchmark. We release a benchmark which does compare Shark with Impala, which it's this clean slate design of a parallel query engine. And we also, of course, we compare with Hive. So I think that this kind of benchmarks will hopefully make the comparison more meaningful. And the benchmark we released, it's open, so everyone can add new queries or new frameworks to compare against.
In the streaming, the Spark streaming part, you mentioned can compose in the smaller and the batch job. And is that the batch job can be represented into some of the language, or is that your operator? How that one to be?
We do have an interface which provides a streaming interface at a high level. But this streaming interface at a high level basically compiles in these repeated batch jobs.
So I think I'm not quite sure is how you guarantee that it will be very short, the batch job. How can you guarantee it's very short, run very fast?
How you guarantee the very short jobs? So it's again, the data is in memory to start with. We have a very low and optimized scheduler. And that the other observation is that job is small. It cannot write and create a lot of data. So in some sense also you bounce the communication.
I think Rakesh has a question here. So if you can get the microphone here. Oh, is there a question there? Okay, sorry. So go ahead, let's finish that, and then Rakesh here.
Hi, Arnab from Ohio State. So just following up on Bill's question. So we're getting faster. Is there a limit do we want to be only so much faster? Because what is 1 nanosecond? Is that a limit? Or what do you think is fast enough?
I think faster. It's a good question. So I think there are two, at least from my experience, I'm talking from my experience, there are two applications which, for which faster is good. So one, it's actually, if you think about, you explore, your exploration. Now you have users and exploring. But actually, you can think that you can have automatic exploration of a large parameter space. This is what you do in some ways machine learning. Like any algorithm has these parameters. So I think the more jobs, the more operation you can do per second, the more you can explore, the higher qualitative, the higher quality results you are going to get. The other thing is that when you want, like denial of service attack, or I can give you another example, maybe it's a little bit longer, but it's from what I see at this startup, Conviva, where you need to make decisions in real time about what is the best bid rate and CDN for someone which comes in. You need to do very fast decision because it's in the user visible loop.
Yep. Okay, let's do Rakesh and then that's.
This is absolutely fascinating talk, Jan. So consider the streaming environment. Can you say a little bit more about for what kind of operations, under what kind of operating assumptions, you can hope to have bounded errors?
What kind of operation?
and under what sort of, because if you have a large drift, you cannot have bounded errors clearly.
Yeah, so far, in terms of the operation, I think we do, typical aggregation, filtering operation. In principle, because it's a batch, you can do very sophisticated operations. And now the question is that can you guarantee the bound, right? I think it's, again, we don't do anything magic on that side. So, and I think that the biggest things we are worried about is about load balancing. That's one of the big things about it, as the data is the data imbalance. You have a popular queue or things like that. And the other thing we are doing is exactly this. There is a trade-off, though, right? What happens, if you have there is a duality there. If you have a hard deadline, you want to produce a result every second, then there is a possibility that you may ignore this and you gave a partial result. Now the question is that what you can say about that result in terms of the error. Maybe that's biased. So I think that's another thing. But it's, again, to answer your question, I think that still quite open what you could do and how you can do. One thing, what thing we do, though, right now we are trying, and this is ongoing research, we are going to kind of the batch size, to adjust the batch size. Because with each batch size, there is a fixed cost of scheduling and so forth for each batch. So you can increase the throughput in most cases if you increase the batch size, right? So maybe depending on semantic of your application, maybe you still want to maintain the exact answers, and it's fine if you go from 1 second to 2 seconds, okay? And also, let me say one last thing. So this streaming, just let me say up front, this is like for hundreds of milliseconds. This is not for Wall Street. It's not for microseconds, right? So it's totally different region.
Can I just make a quick follow-on observation?
Please.
Why I asked the question?
Let's use the microphone.
I'm sure there is
So we kind of looked at a bunch of Twitter streams. And as you change the window sizes, we're just trying to figure out, are there some deviations or expectations things are happening? And you vary the window size, the results change dramatically.
I would expect.
And if you're trying to now do it in real time, I'm sort of very concerned about the errors that you could be making.
But here it's again, that's a fine point, but here it's again, you can have and you can provide operation at the same time in the same system over different time intervals, and you can pick one. It's perfectly compatible with the system.
Can you end like 10 to 4? Let's take that as a final question.
It's a very long question. No, quick ones. Now, I'm actually intrigued by your choice of the response to the problem that even in memory is not fast enough for interactive tasks. And this is a problem that is shared by large areas. And what I was surprised by was your choice of trading a quality instead of looking for hardware support. And the reason I was surprised is because we have been looking at the problem of trying to do error bounds on approximate error results. Incredibly hard problem, probably much harder than customizing hardware. So why couldn't you just...
I think Surajit will agree with that. So I think, yeah, it's a hard problem which makes a good research. Hopefully there is a feasible answer. So I think, look, I think that the time for that, it is now. I think people, they are doing sampling today in an ad hoc manner everywhere. Look a little bit at the data, try to infer what happens, right? And the reason is that if you look from the decision perspective, there is a time component. If I can give you the answer in 1 minute, even if plus minus 10% with 95% confidence interval, it can be much more valuable if I give you than if I give you an answer 1 hour later. The other component is that the data comes in, has a noise. Many, many data. So if you have an error, say with the data which is the input, plus minus 1%, if I give you the computation which is 0.1%, you add to 1%, it doesn't have a qualitative answer. It's not like the truth in the database and it's zero error if I do the computation of the database data, and then I do the approximation, I have an error. So it's error, no error. Here it's error, a little bit more error. But yes, it's a hard problem, especially if you go through this kind of more general computations. And that's why one thing I mentioned, but it was pretty fast, is that one thing you want to look at to diagnose. Even if you have the closed formulas, even if you have that aggregation operators. We look on the data at Facebook, and you get an error, and actually it is not true, right? Even if you apply the closed formula, because the closed formula are asymptotic in nature and make some assumptions, right? It's not of a fixed sample. So I think that diagnosis, in order to make it work, is extremely important.
So the other small thing to add is, we see it everywhere, that even if you use specialized hardware, for any given number of hardware, you'll max out. Okay, so you'll always find this, if you can, and I think your point is very true, it's a very hard problem. If you can, they would always be very helpful. So, all right, thanks a lot, Ian, again. So the final talk in this session is from Vivek Narasayya, who has been my colleague for a long time, and he was a founding member and, in fact, had a leading role in the AutoAdmin project, which is to make database self-tuning. And he has a VLDB 10-year Best Paper Award, and he did his PhD from University of Washington, Seattle. He's a principal researcher currently in XCG, Microsoft. With that.
Thanks, Surajit. So I'll see if I can get you on time for your coffee break. So as Surajit said, this is sort of work that was done here at Microsoft Research with the colleagues listed here. But I also want to mention, many of you here are faculty members. Really, the interns who came in and worked with us played a very significant role in these projects. I do want to acknowledge that. So what is the setting of this work? That we have these multi-tenant cloud data services. An example of this would be something like Microsoft SQL Azure, where we have a classic relational database running as a service in the cloud. Amazon RDS would be another example. And then on the other side, you have these other MapReduce platforms, also available in the cloud for doing these big data kind of computations. An example would be Amazon's EMR or Windows Azure HD Insight. Now, if you ask the question that when you look at these platforms, the tenants of these platforms are sort of one side of the equation, and then the other side you have the service providers. And there's a fundamental tension between the cost and the performance that tenants and the service providers see here. So from the service provider's perspective, they want very low operational costs. So and how do you achieve this? By sort of packing a lot of tenants onto the available machines. And of course, from the tenants side, they want excellent performance. And so how do you kind of do this trade-off in a way that's acceptable to both sides. So in other words, what should sort of be the contract between the tenants and the service provider? So that's the issue that we are going to look at here. Let's pick one of these platforms, which is the database as a service. Let's just see what the setting looks like in the data center. So if you look at a particular machine in the cluster, you're going to have a database server process running there. So it could be SQL Azure running there, and within that you might have databases of multiple tenants, and these tenants are going to be running their SQL queries. And so as you can imagine, these database systems were never designed to be multi-tenant from the get-go. In other words, all the queries that one tenant issues could very well end up having an adverse impact on the workloads of another tenant, on the performance of another tenant. But intuitively, tenants want to kind of be isolated or shielded from which other tenants actually may exist in the system. Now, if you look at multi-tenancy in the MapReduce platforms, let's sort of draw an abstract picture here. You have a very similar picture. You have tenant 1 submitting a job, there's some kind of a master node, and then the slave nodes are actually going to be doing the work. Each task at the end is simply an operating system process running on each of these machines. And just like in the SQL case, you could have one task, could be doing arbitrary work, could completely trample on the performance of another task. So once again, the same issues. And if you notice here that there are sort of different levels at which you may want this isolation, both at the task level, at an individual task level, but also at an entire job level. So today I won't be able to kind of get into specific solutions for both these platforms. Sort of in the interest of time, I'm going to just focus on the relational database as a service. And many of even though the challenges are similar, the solutions actually tend to be quite different in our experience. So today, in other words, I'm just going to focus on this project called SQL VM, where we looked at what does multi-tenancy and how does performance isolation work in the multi-tenants database as a service. So you could ask the question, what are sort of the requirements? If you are, want performance isolation, what does it mean? What are the requirements? Intuitively, a tenant doesn't want to know which other tenants are running on the cluster, and that should not affect my performance. On the other hand, a trivial way to achieve this would be to just statically allocate resources for each tenant, and effectively, by virtue of that static allocation, completely isolate one tenant from the other. But this is not cost effective from the service provider's standpoint. So for example, in the databases, you could say, why not just take one virtual machine, run the DBMS process within each of these VMs, and let the tenants use the resources. But this doesn't scale, because now within each VM you have an OS, you have a DBMS, the fixed overheads are just going to kill the consolidation you can get. The third point, which is really very, very important, I think, is the notion of accountability. So when I run my app with a workload in the cloud, I do want the service provider to be accountable for this performance isolation. It's all too easy to say you have isolation, but then how do I know that I actually got what you promised me? So you could ask the question, for a database workload, why don't we think in terms of performance isolation in the form of queries per second or query latency? This seems like a very natural thing to do, except that let's take a look at this simple example and convince ourselves why this is incredibly hard. If I give you this query, it would take a certain amount of resources to run on the system, but all I have to do is to change one constant here, and you can imagine that the amount of work done by the same query could be vastly different. So when I say queries per second, it's not even clear which query we mean here. Although, of course, that would be a great thing to achieve if we could somehow promise that, but that sort of still remains an elusive goal. To complicate matters more, the database as a service providers are trying to tell the application developers, please come in, write your applications, we'll be backward compatible with every app you've written before, and you could even submit ad hoc queries. So this problem becomes incredibly hard for a platform. So our approach, in some ways, which we call a SQL VM, in some ways you could argue is a step backwards. We are going to be looking at what people do today with your enterprise servers, where you have actually a physical box under your desk where you're running your workload. And we say that, can this abstraction be made possible within the cloud setting? Okay. So the advantage of this, of course, is it's very transparent. People still know what this means, but it's just that now the cloud is responsible for the same contract. So think of it in some ways as a logical virtual machine, but running inside this SQL Server process, for example. And what are you getting? What you're actually getting is a reservation of resources within the SQL Server box or the database server box in general. And so what does this mean? In terms of sort of the technical issues, what does this mean? The first thing is that we need novel resource governance mechanisms inside the database engine. They were never designed for this kind of a setting. The second, which goes back to the accountability problem, is when I promise you a certain IOPS for your workload or a certain CPU utilization for your workload, how do I know that the service provider actually delivered? So I'll touch upon these very briefly in turn. So the first thing is, let's take a situation where you have two tenants running. There's plenty of resources capacity, in this case IOPS, but the tenant 1 has been promised 100 IOPS and tenant 2 has been promised 50 IOPS. When I say promised, what I mean is this is the minimum IOPS that the tenant has been guaranteed. You could also have a corresponding maximum, but I'm just skipping that for brevity here. So without getting into details, there's a number of technical challenges in providing this abstraction. So for example, if you have tenant 2, it would come in with a very big bursty I/O workload and completely swamp tenant 1's workload if you're not careful. So the question is that how should you do resource governance to make sure that each tenant first gets its minimum and then any excess capacity may be then shared in a certain way. Okay? So those mechanisms need to be built in. And sort of here we are using the idea of sort of shaping the traffic. So we're going to say we're going to queue the I/O requests and we're going to issue them with a certain deadline. So when an I/O request arrives, if I promised you 100 IOPS, I know a certain point in time by which this I/O should be actually issued in order for you to reach your rate, promised rate. So we're going to track that. And the flip side of the resource governance is the metering. But this is also super important. So here's the challenge. So if let's say I've promised this tenant 100 IOPS, but in a certain interval we achieved only 80 IOPS. How do you know which of these two situations actually happened? Either the tenant could not have had enough workload to achieve 100 IOPS, or we as a system provider didn't actually give you even though you had the workload. How do you fundamentally distinguish these two? And so the basic idea is that, which I'm going to illustrate through this example, is that as soon as an I/O request arrives, we're going to determine a certain deadline, by which point, if that I/O is not issued, we know there was a violation. Okay, so inherently the system provider, no matter what the resource governance mechanism used may be, the scheduling algorithm may be, the metering logic will be independent of that, but we'll always be able to say whether you met the contract or not. So this is just one idea for for I/O. The CPU problem and the memory problem are quite different. Today I won't have time to sort of get into that. Now you could argue, what is the value of metering? What am I going to do with this metering? Today, if you look at something like availability, you could go to Amazon EC2 and they give you an availability contract. They say that if you don't meet your availability, you could have some kind of penalty associated with it. And a similar model can apply here. So you have this notion of metering, which would detect violations, and then you can actually have a penalty associated with that. Now, from a service provider standpoint, let's say we have these kind of SQL VM-like mechanisms in place. Now it enables a whole bunch of interesting scenarios. Just like in your airline, where you're going to, in order to sort of lower your cost, you're going to do some amount of overbooking and then hope that not everybody actually shows up that day. A similar strategy now becomes possible. So what I can say is that in this case, I have only a capacity of 200 IOPS. It's a toy example. But I can actually promise each of them slightly more than the actual available capacity in aggregate. And when in a worst case scenario, it could be that both the tenants do indeed come up with their full workload. In that case, something has to give. So we won't be able to meet perhaps one of them or both their contracts. But that does open up the question of, it's an optimization question, how should I allocate my resources in order to trade off both fairness to the tenants as well as my own cost, the service provider's cost. So you can think of this as sort of an online optimization problem. And these are sort of new things that open up in this world where you actually have promised a certain performance guarantee to the tenant. Now, you should think of everything I've said as sort of being a building block. This is not the end in its own right. There's a number of interesting and related technical problems, such as how many tenants should I place on a given node? And then when, I also have levers like load balancing or tenant migration, when I see that perhaps this node is not in a sustainable mode anymore. Right? So those are very related problems and need to be addressed to solve sort of the bigger picture. So I'll briefly comment on CPU and memory, just to give you a flavor of why they're somewhat different. So in the world of CPU, what we're promising the tenant is to say that I'm promising you, let's say, a 10% slice of the SQL Server's CPU on this machine. And similar, just like we did for I/O, the metering has to come and say, can distinguish between the sufficient workload or the insufficient workload and when the system messed up because it couldn't do the allocation as promised. The technical details of this are in a VLDB paper. And indeed, there are a lot of similarities to a whole bunch of scheduling work that has been done in, obviously, it's a very old topic, like real-time operating systems have done CPU scheduling. But there are some key differences here in this setting. One of it being the metering, and the second of it is that if you look at database engines, the schedulers are non-preemptive. So often when you when you schedule a query, it could take a very high amount of quantum before it yields the scheduler, which means that you have to be able to have techniques to deal with these highly variable quantums, for example. Memory is actually a very different kind of resource, very different than both CPU and I/O. And you could even ask the question, what does such a contract mean for memory? How should we think about performance isolation for memory? And one observation here is that if you look at something like a buffer pool in a database system, we can think of it as a cache of the pages of the tenant's database. And what do I want? So the obvious thing would be to say, hey, just reserve this 1 gigabyte of buffer pool for me and just hold it for me. But that's not very cost effective, as we saw. Another model could be to say, what I really want is I want the same hit ratio as I would have gotten with a 1 gigabyte buffer pool. And that could be your contract. Right? And now, of course, this opens up some interesting questions. How do I even do the metering in this case? I would have to know that for the same tenant's workload, how would I exactly know what would have been your hit ratio with a 1 gig buffer pool and then what you actually got? Now, this is something that we have done. And this turns out to be feasible. There are some overheads that you incur. But I think that's sort of expected when you have a multi-tenant setting, that you would incur some overheads. So at this point, I thought I would show you a very quick demo of the system. So if...
So you want to comment on where it is on the product cycle? Or?
Yeah, I'm going to say that in a second. Yeah. But yeah. So here, what I'm going to do is I've just opened a Windows Server box here, and for those of you who may not be familiar, what I'm showing you here are what is called the performance monitor, perfmon, which just looks at various counters that we expose from the system. And here we have I've opened 4 such counters. I'll show you what they are in a second, but let me first start executing the workload. Okay, so here the setting is the following. So we're going to run 8 tenants, each of them running just sort of a CPU and I/O intensive micro benchmark. So the queries are very, very simple. They just do some number of CPU loops or some amount of like a range scan of a query. So they're going to incur some I/O, and we're going to have one tenant of interest. Okay, so think of this as this is the tenant whose performance we want to preserve, have a good performance. And then we're going to introduce additional tenants running identical workloads into the system over time. So here in this performance monitor, what I'm plotting is the end-to-end throughput of the tenant of interest who's shown in red. So you can see that initially when you started running, this tenant had a performance throughput around 5,000 queries per second. But as other tenants started coming into the system, the throughput began to decline pretty sharply. And after about 8 tenants have come in, you can see that its throughput has dropped dramatically. So this is sort of your classic noisy neighbor problem in multi-tenant systems. And here I'm also showing you the latencies for the same workload. You can see that the red tenant's latency has been climbing up sharply over as other tenants come in. So here, no great surprises so far. If you go back and look at what's happening in terms of the resource usage, here I'm showing you the CPU utilization of tenant 1, which has dropped dramatically. And this is also showing you the disk reads per second done by tenant 1, which has also been dropping dramatically. Okay, so this is what you would expect in a system which has, which has no sort of the SQL, it doesn't have the kind of resource governance that we talked about. So now I'm going to just run the exact same setting, the same workload, but in this case, I'm going to turn on SQL VM. And now we'll try to see exactly for the same setting, how does tenant 1's performance look like. So here tenant 1 has started executing, and it's settling down to around the same number that it had before, should be around close to 5,000 transactions per second. And now you can see here the second tenant has started executing. And if you notice, tenants 1 throughput is still pretty solid around 5,000. But note, interestingly, that even the latencies are very, very low. It remains exactly the same as it was earlier. And now if you want to try to understand what's happening, let's go back and look at the actual CPU and disk reads per second. And if you, let me just move this here, you see that the CPU utilization has remained pretty constant around 60%, which is what the SQL VM setting was for that tenant. So this is just to give you an illustration that how by using this building block, you can absolutely isolate one tenant from the other. Okay. So I'm not, in the interest of time, I'm going to skip related work. If you guys have questions, I'll be happy to talk about this offline. But there has been obviously a bunch of work in both the database literature, but also the broader systems community in this area. So just to wrap up, this is my concluding slide. So the I/O resource governance work that I just talked about very briefly here is now part of the SQL Azure product. So they're going to already begun rolling this out, and so tenants can take advantage of this facility. Turns out that even for your classic on-premise workloads, you just have a bunch of applications running within your enterprise, you may want similar isolation across different applications. And so the SQL Server, the box product, which is coming out in SQL Server in 2014, released a CTP1 just last month, which also has the same functionality in it. I sort of hinted along the way at some of the ongoing and the future work. But for example, overbooking, how do you do capacity planning in this world? And whether we can aspire to give some kind of higher level SLAs at the level perhaps of the application still remain some open questions. So with that, I'll take your questions.
I'll ask him. I'm not a author of that paper. So
yeah, Jignesh.
You want the slide deck presentation?
Do you have some thoughts on, you started by saying the resource governance for SQL is a different problem than resource governance for MapReduce. Some of the cloud providers use VM, and like VMware, for example, has shares and limits as a way of using a mechanism across the board for applications. Do you have a sense, if you're just talking about databases, would a VM-based approach come close to that, or are there things that you can do with the VM outside the SQL engine itself?
Right. So there are reasons why you may not want to use a database in a VM. I alluded to some of that during the talk. But let's say you did want to do that. Even to the best of my understanding, the hypervisors don't have, A, they don't have the accountability, the kind of stuff that I talked about. And B, for memory, for example, there are things like ballooning that VMware has done, but it's not, in some sense, principled in the sense that I, as a tenant, it's not transparent to me. I don't know what's going on under the covers, right? And so, maybe it's doing a great job for the system as a whole, but it could totally mess up my performance. I have no visibility to that. Similarly, for I/O and CPU, I think that the right mechanisms are still not there. Okay, so if you want, let's say I have a very bursty workload, and I want to kind of have guarantees that my burst would be met. This is not something that I think most of the hypervisors provide today. I don't claim to be, fully conversant in all the related work.
We can talk offline. Yeah. Thank you.
Any other questions? Sang? Yeah. And then Amar. Yeah.
So actually, maybe I'm addressing the last bullet point, high-level performance SLAs, which is very, complicated problem. So, database level, multi-tenancy is already complicated, but in the real world, you run the quarterly, results, and you want to have some guarantee, and you run the monthly, payrolls, you want to have some guarantee. Do you have some thought on how you map this, high-level SLAs to database level.
Well, there is some work, or there's some work already coming out in the sense that people are trying to look at a workload and try to estimate how much resources might be necessary for that workload in order to achieve a certain performance. Now, again, this is by no means robust or close to being practical, but that's sort of one trivial way, if you will, to map that question onto an underlying substrate like SQL VM.
Okay, this is a similar vein. It's the side effect kind of phenomena where, okay, so you concentrate on one metric, for example, IOPS, and then you might affect response time or latency. So, how do you have any comments on this?
Right. So I think so. If you look at, so you can take IOPS, you can take CPU, and you can take memory, right? And now these different resources, of course, interact with each other, right? So you need to have accountability for each of the metrics, but I'll just give you one example where the interaction is somewhat non-trivial. So let's take memory and I/O, right? If I don't do a good job with my meeting your memory contract, I could increase your I/O. But the system should not then, penalize the tenant for that. Rather, the system should, absorb that. So how do you do that accounting accurately? That would be one example of the side effects.
Any other questions or comments? One last, if any. Okay, thanks a lot, and thanks for also catching up on time. So enjoy the cruise as well as and the keynote before that. So thank you.